So, right. So we've talked about specific heat, which has to do with just being in a phase because we're changing temperatures, right? So we're going from a solid to a solid, so on and so forth. Now we're going to talk about going from a solid to a liquid to a gas to a liquid, so on and so forth, and how the potential energy is going to change. So the potential energy changes only when you have a phase change. Okay. So when you have a phase change, that's when the potential energy is going to change. That means that the kinetic energy is going to remain the same. It's not going to change. You can't change both potential and kinetic at the same time. Right? So I know we went over this already together, but let's go over it again. So melting, we're going to have an increase in potential energy, and melting is when you go from a solid to a liquid. You're going to have solidification, crystallization, or freezing is the opposite of melting. So both of them happen at the same temperature, right? So for whatever it is, for water, it's specifically 0 degrees Celsius, is both the melting and the solidification phase. Okay, but during solidification and crystallization, the potential energy is going to decrease. Okay, when you have a phase change, you're going to have both phases present at the same time until that temperature starts to change again. Okay. So for vaporization, when we go from a liquid to a gas, our potential energy is going to increase because you have to add heat. Melting and vaporization, you had to be adding heat the whole time, so therefore potential energy will change. Okay. Condensation is when you go from a gas to a liquid. And so you're cooling down and the potential energy is going to decrease. Then you have sublimation. Sublimation is when you're going to go straight from a solid to a gas. You're skipping over the liquid phase. Now, there are a couple of substances that do this, and one of them is going to be dry ice. Dry ice is one of those things that you cannot handle with your bare hands. You have to be wearing mittens because you can actually burn your skin. Not because it's hot, but because of the way that it reacts with the water on your fingertips. All right. And deposition is going to be the opposite of sublimation. It's when you go from gas to a solid, skipping the liquid phase whatsoever. And again, the phase change is, or the potential energy is going to decrease. Okay. All right. So let's see if this FET will actually work. So let's start with the states of matter. Okay. Actually, before I do that, I'm going to take over on my iPad really quick. Okay. And we're going to do phase diagrams. Before we do like a phase change diagram, I want to specifically talk about what it looks like for the molecules in a solid, in a liquid, and in a gas. So what I want you to do is draw 3 boxes. Okay. Is there a way, guys, to copy something? To copy a shape?
You take the scissor tool and you circle it.
Okay, so you circle it. Ah. Now what?
Duplicate.
Where does it say duplicate?
You have to click on it.
Aha. Thank you. Okay. Can I move it? How come I can't move it now?
You have to only move it when it's still circled.
I'll move it now. Aha. Thank you. See, you learn something new every day, and you guys know this stuff way better than I do. Okay. So, we're going to start with a solid substance. And then we're going to go to a liquid. Okay, and then we're going to go to a gas. So what should they look like? These are what's known as particle diagrams. Okay, because what you are doing is you are showing particle diagrams. I can write really badly on here. Okay, and just like anything else, you're going to want a key. Okay. I will explain what those things mean in a second. Should I write single atom or should I write monatomic? Let's do with okay. So I want you to set up yours to look like mine. Does everybody have theirs?
Almost.
No,
Okay.
hold on.
Okay. That's why I asked.
Wait, what does the second one say on the key?
Diatomic.
Okay, thank you.
No problem. Okay. So what is the difference between monatomic and diatomic? Well, if you're looking at it, if it's a monatomic, okay, it's one. I gotta make this circle better. It's bothering me. Okay. Okay. It's one single element. Okay. If it's diatomic, it's two elements or it's two of the same element bonded to itself. So something like oxygen, okay, something like oxygen in and hydrogen in at room temperature will be bonded to itself. So that's why there's just two circles there. You'll learn more about that next year, but I want to throw those vocabulary words out. There's only a few elements that actually are diatomic in nature, and you'll see them bonded to themselves. Okay, so when we're looking at a solid, we said that solid, let's just make life easier, one big dot. Okay, that solid, right? The atoms are super close together. They are structured, but they're still moving, but they can only vibrate. So when you draw them, right, you're going to draw them where they are super close together. They are basically in a pattern. Okay. They should be in a structure. They should be super close together. They should be in a pattern, right? In a liquid, they're not, so they can only vibrate in a solid. In a liquid, they're going to be more fluid. They're not going to be as organized, right? They're going to be a little bit more crazy, just a little bit, not by much, right? But the main difference between a solid and a liquid is the fact that you have these spaces in between each of them. Okay? In a gas, it has to be a closed container, but it fills that container in a random pattern. Okay? Gases, I like to explain them like they are a kindergarten class you just gave a ton of Halloween candy to. Okay? They look like an out of control class of kindergartners. They're all over the place. They're swinging from the chandelier. They're bouncing off the walls. They're bouncing into each other. There is no controlling the chaos in a gas. And believe it or not, that's what everything wants to be in nature. They want to be chaotic. Okay. So if we go back to the PowerPoint, does everybody have this?
Wait, so copying.
Okay.
Yeah, I got it.
Thank you, Keith.
Okay, I'm good.
Okay. So, like I said, going back over here, right? And we're looking at our states of matter. You see how something like neon, right? These are the molecules over here. These are what's known as FETs, guys. They're PHET.
Miss Gonzalez,
What's up?
this screen is like black.
Black.
I see your screen though.
I see it. It's fine.
I see it.
Yeah, me too.
I'm a join.
Cassie
Yeah, I
is
see it.
black.
On my iPad, it says it's fine. Go back, go out, and come back in.
Okay.
Is this website linked on Google Classroom?
No, but I'm about to give you the link. So what I'll do is I'll go into the PowerPoint, grab it. Go back. Grab this. So if you want to play around with it, it is right here for you guys. Okay, if you want to go into it right now, we're just in the states part of it. Okay, so neon or argon, basically they're going to play the same, right? They are monatomic elements. You see they're represented by one dot, right? And right now we have the solid version, right? Versus the liquid version. You see how they're a little bit more chaotic, but they're mostly staying to the bottom. And then the gas version, they're all over the place. Same thing with argon. It doesn't change, right? It's the same simple, easy way of doing it, right? Oxygen, like I said, is one of those diatomic elements, right? They're the same thing bonded to itself here, right? In the solid form, they're still really close together. They're still just vibrating. In the liquid form, they kind of look like ants on a hill, okay? And in the gas form, they're all over the place, okay? For water, water's kind of the pink elephant in the room. And the reason we call it the pink elephant in the room is because for a gas phase for water, they're the same. But we know that solid water actually has a lower density than liquid water. How do we know this? Because of the fact that solid ice floats in water. So water's molecule itself kind of looks like Mickey Mouse, right? You have that red colored oxygen in the middle and the two hydrogens on each side, kind of looks like Mickey Mouse, okay? But I want you to look. In the liquid phase, just like a typical liquid, right? They're still spread out enough. They're not crazy close together. But here's the thing. in the solid form, you see all of that extra space in between each of them? Okay, that extra space lets air get trapped in it, which makes solid or ice water, okay, actually going to be less dense because it has that space. So look at the difference. So we call water the pink elephant in the room because it does not follow any of the whatchamacallits that any of the rules that any of the other ones do. Okay. Let me see if I can go back to this real quick. Now, if we're talking about phase changes, right? It's if you heat it up, what starts to happen? It starts to move away, right? And then eventually it'll become a gas. And if you cool it, it does the opposite, right? The molecules or the atoms start to get closer and closer together, just like we've been saying, right? And you see how they get closer together, which means they're going to get more dense, right? And they're back in their solid form. Just something to show you really quick. All right, so the last thing we had left off of was a phase change diagram, and I'm going to take over again on my iPad. Okay, so I believe the other day when we were doing this, I called it a PE diagram. I'm sorry about that. It's not actually called a PE diagram. It's called a phase change diagram. Okay, I realized I made my mistake, right? And before you left, I had you draw this when it comes up. Yes? You guys remember me saying that?
Yeah.
Yeah.
Okay. So when you are looking at the phase change diagram, okay, first of all, this one is when temperature is going to increase. So this should be temperature over here. And we'll say it's in degrees Celsius. Okay. Down here is just going to be time. We'll say it's in minutes, right? Because, of course, if we're doing a diagram or a graph, you need to have the axes labeled. We need to have the title that is there, which is our phase change diagram, right? You guys are losing points constantly during the labs because you're not doing that. Okay. So as you can see, it kind of looks like a step, right? Kind of looks like some steps. Okay. When you're looking at this so far, while we've done any of this stuff, I just introduced you guys to the potential energy not changing during phases, right? So that's where these plateaus or flat lines are going to be. Okay, so these flat lines are going to be where your phase change is going to happen. Specifically because we're heating this substance, this is where melting is going to be. Okay, and we said melting is going to be where we go from a solid to a liquid. Just letting you guys know that is a script L. I learned it that way in chem many, many moons ago, and it's been ingrained in me ever since. You can write it as a straight L. A lot of times people are going to take that as a 1, so just be careful with that. So what happens during melting? That means we have a change in potential energy. All right? So since we said melting happens here, that means in the phase before it, right, if we're looking here, this would have to be where the solid phase is. Okay, why? Because it comes before melting and it's at a lower temperature. Okay, this is where you're going to have your kinetic energy changing. This is where you're going to have your temperature. You can obviously see on our chart here, right, that temperature is changing. That's why it's an increase or a slanted line. When it's a plateau, it means that it's not changing. Something's not changing. Okay? So when you have melting, your particle diagram is going to have both the solid and the liquid phase. Okay, so we just did particle diagrams for just the phases. If we were going to do them for a phase change, okay, so let's say this was melting or freezing. Okay, if I'm going to melt or freeze this, I'm going to have both the solid phase. So I'm going to have a very structured. Why aren't you coming out larger? Okay. All right, I'm going to have some solid. And then also some that break off as liquid. Okay. Versus, okay. If I have a particle diagram for when I go from just easier a liquid to a gas or a gas to a liquid, right? Right. I'm going to have some particles down at the bottom and some up top as well. So you're going to have both of them at the same time. It's kind of like you just merged one right on top of the other. Okay, so during a phase change, we have both phases until, okay, once the substance starts changing temperature again, right? So it's going to go through this entire thing until it reaches right here, right? Once it starts to change the temperature, it means that you only have at this point the liquid phase. Okay. Once you start changing temperature, that means that's the point which no more solid is there because it's all liquid. And now we're back to our kinetic energy changing. Okay. And you'll notice in this that the liquid phase line is much larger. It is done for a reason. Okay. The difference between 0 degrees and 100 degrees is a lot. Okay. So you're going to remain in the liquid phase between 0 degrees Celsius and 100 degrees Celsius. Okay. Up here, also, there's a difference between the melting line and the condensation or vaporization line. Okay. The reason for that is it's going to take more energy to vaporize something than it is going to be to melt it. Okay. And we're going to have a change in potential energy.
Miss G,
What's up?
why on the straight line is it vaporization, not the when it goes up?
Because remember, if we're not changing the temperature, right, that means we're going to change the potential energy.
Oh.
Because average kinetic energy is temperature. So anytime there's a solid, a liquid, or a gas, and at this point I could just write in that this is the gas, right? They're going to be on the lines where you have a temperature change.
Okay.
Okay. So as long as there's a temperature change, that's going to be indicated by a diagonal line. you can have the phase by itself. That's going to be, guys, just so you know, and I would, for those of you who are planning on going to chem next year, I would take a picture of this and save it when I'm done, because you're going to do this exact same thing with the calculations next year. Okay? Anywhere you have a solid phase, we've already talked about those Q equations. We've already talked about this is where we're going to have our specific heat change, right? This is where we're going to have we're going to use that MC delta T, right? It's going to happen where you have a change in kinetic energy, right? So this is where MC delta T, you could use that there, and you can use it here. Okay, so far this is what we have. Okay. So before you ask me, yes, there are two other formulas that you can use. Okay. One's going to be for melting, one's going to be for vaporization. This one is called the heat of fusion formula. So it's going to be MH with a little subscript of an F. Okay. Where HF is the heat of fusion. Okay. And just like C is specific heat of fusion and what's known as the heat of vaporization are specific for everything. Okay. So we have the heat of fusion and we have the heat of vaporization. So fusion is going to happen at the melting point. Vaporization is going to happen up here where you vaporize something.
Miss Gonzalez,
What's that?
what was the formula again? I missed it.
For which one?
Oh, like I thought like you wrote like a formula like M equal like something like that.
They're all Q equals because they're heat formulas.
Oh, okay.
Like Q equals MC delta T, Q equals MHF, Q equals MHV.
Can you zoom in to
Which
like
part?
the graph?
The graph? Sure. Is that better? Do you need it zoomed out, zoomed in? What do you need?
Yeah, that's good. That's good.
Okay. Okay. Now, in this case, kinetic energy and potential energy is going to be increasing because you're going from a solid to a gas. So you had to add heat to it. Okay. But in the chance of cooling, you go in the opposite direction where you go from a gas to condensation to a liquid to freezing to a solid. So it's literally just the mirror image of it. And kinetic and potential energy would change at that point. Okay. Does everybody have this?
No.
Okay. Because I have to show you the reference table really quick. Kia, you okay? Kazmira, you okay?
I need the bottom, like, of what's under the graph.
The heat of fusion versus heat of vaporization?
Yeah.
So HF means heat of fusion. HV means heat of vaporization.
Okay, got it.
Good? Awesome. All right, so everybody look at your reference table really quick. So yesterday we were talking about this one, right? This chart. Oh, where'd it go? It just disappeared on me. All right. I want you to look right underneath it where it says properties of water. If you look right underneath it, right, it talks about heat energy gained during melting and heat energy released during freezing. These two here, okay, the melting and the freezing, okay, those are going to be your heat of fusion for water. So it will take 334 joules of heat per 1 gram of water that needs to be taken in order to change it from a solid to a liquid. Okay, I'll say it again. So for water, this is the constants for water, all right? You need 334 joules of heat okay, to melt 1 gram of water. So you need to absorb 334 joules of heat to melt 1 gram of water. Remember how when we were watching the video yesterday, I said that that Mr. Hammock over there, or from Hammock's Middle School, messed up with the units because he kept saying 4.18 joules per gram. It's not. When you're talking about joules per gram, you're talking about no temperature change, okay? Which is this. This is not changing your temperature, okay? Because there's no temperature there, right? So if that's how many grams you need to melt and take in 1 gram of water, that means you need 334 joules to be released in order to freeze 1 gram of water. Okay, so that's the heat of fusion. For the heat of vaporization, you're going to use 2,260. When you go back to your phase change diagram, right, I said to you, come on, that there's a reason why the line for vaporization is much longer than the line for melting, because it takes 2,260 joules of heat to vaporize water. So it's a lot more than the meager 334 joules to melt it. Okay? So when you're looking at it, right, to melt something or to melt water, you need 334 joules, whereas to vaporize it, you need 2,260 joules. Okay? You need a lot more energy absorbed to vaporize it, and you need a lot more energy released to condense it down. Okay? So what I wanted to show you really quickly before you go is, hold on one second. Here we go. Share. Is this version, this little animation. Okay? This little animation has everything we just talked about, but what it has is it also has the phase diagram on the top, right? That particle diagram showing you both the solid and liquid phases happening at the same time during melting, and both the gas and the liquid phase happening during whatchamacallit. And I'm going to post this right here for you guys so that you have it. Okay. And I think that's it. I will post for you guys your homework in your review book tonight. It's these practice problems. It's pages 93 to 94, questions 31 to 48. Okay, so I want you to complete those questions for homework tonight. Okay. And class is over, guys.
I have a question.